Hello everyone, today I'm going to show you the fastest and most elegant approach I know to create a 3D grid in Blender Geometry Nodes with a lot of options to change the size, the resolution, the X, Y positive, to change the radius of the points of course, and the option to fit it to the size we set to the exact size. Um, Also, you can preview the domain of the points, so you can see the domain, so you won't need to calculate all the points all the time, which is much faster to use. So let's get started. By the way, I'm working on an add-on with a lot of super useful geometry nodes, and this is going to be one of the included there. It's going to be called H nodes, and it's already in alpha stages, so stay tuned for that. So let's fire up Blender and get started.
So let's start with a fresh Blender scene and open a new window, set it to geometry nodes and create a new geometry nodes tree. I already pinned this tree, so won't need to worry about it going away for some reason. And let's start. I want to start by discussing a few other methods there are to creating a 3D grid. The first method is the grid method. By using an actual grid, let's plug it, and we can, if we go to wireframe, we can see we have X and Y, and we have a bunch of the controls to control the X and the Y. And the way to create a 3D grid out of this 2D grid is just to use an instance on points. Use the grid as an instance and use a line mesh line. Let's plug that to the points, set it to endpoints instead of offset, and we have points. There are a few problems with this method. The first one is that you need to generate a grid. The problem with that, it's not a very big problem, but from my experience, is way slower to generate grid. When you just need the points, because when you generate grid, you also generate faces and edges that are not needed. From here, you can use mesh to points to convert it to points. But it's important to remember that you're using instances and not actual points. So let's say you want to use a noise, and let's edit delete geometry. So if you try to delete some of it, so let's do a compare note just to preview what's happening. You see that here can't erase points in the middle because they're instances, whole instances. So you can actually take a realize instances node, just plug it, and you get your points back. Of course, this is, in my opinion, less elegant and less fast solution. So the second solution is actually quite the same. The only difference is that you use mesh lines to avoid creating faces. So let's take 3 mesh lines, one for each axis, and let's set the first one to be X, the second one to be Y, and the third one to be a Z. So let's instance the Y on the X axis. So let's see how it's look. So we just take a basic line, his points, and we instance the Y line onto it. So we have a lines instances online, and now we can do the same thing for the for the Z axis on the points instances. So we have the same result. And again, it's instances, so you only have these planes. And if you want, you can realize it. And it's pretty efficient. Not the most efficient, but it's pretty okay technique. I personally prefer to use a technique that doesn't involve instancing. And now we're going to discuss the other technique. This method also used by Arundel to create a 2D grid. And I don't know if you made any tutorial about 3D grids, but this is what we're going to do today. So let's start by taking a line mesh, and we're going to use only the offset, the count factor, because the direction doesn't really matter. We're going to change it later. So let's preview that just by using a line on mesh 2 points, and I'm going to also add index viewer so you can view the indices. So now we're going to take you're going to use the index of every point to decide what position it should have. So for that, let's add a set position node. So the set position node allows us to set the position and the offset. We're not going to use the offset. The offset is basically just like the position, just with a vector math set to add. So you can replicate that by taking a position and a vector math, like the position to first input, and this exactly like the offset. It's offsetting from the current position. So let's take a combine x, y, z, and if we plug the position to the combine x, y, z to the position, we have a single vector that we can control. So the first thing we want is to take an index viewer. Let's plug it just to the z-axis. So you can see here that we have points with the index of 0, 1, 2, and every index is also the x position of the point. So index 0 will have the position of 0, index 1 will have the position of 1, so on and so on. And we can control the count, and it will keep going as far as we have. Let's scale it a little bit larger. Okay. So now we want to set it procedurally. Let's take an integer. Let's call it x. Take another integer. Let's call it y. And for now, we're just gonna mess with x and y. I'm gonna add the z component later. So let's say I want to have a grid by x by 10, or a 10 by 5 grid. So a 10 by 5 grid means that I have 10 on the x-axis and 5 on 5 rows of this x on the y-axis. So we want to have 50 points because it's 10 multiplied by 5 to create this grid. So let's take math, say to multiply. Let's multiply our x bar y, and now we have 50 points all the way up to 49 because the first index is 0. So when we're talking about grids, we're talking about rows and columns. So if you have grid of, let's just make a set of points. So we have an index for each row, an index for each column. So let's say for this, so for the first row, the index will be 0, for the second one it will be 1, and for the third one it will be 2, and so on. And for the columns it's exactly the same, 0, 1, 2, 3, and so on. So what we use is actually just manipulating the indices, which is 0, 1, 2, 3, 4, and so on, to create those. So for to create the index for the x-axis, which is 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. We're gonna use modulo. So let's do that. Modulo. Get a math node. Let's say to modulo, and when you state that every index we have, so we have a first input and a second input. The first input is our index, it's the value, and the second input is on what value it shouldn't pass. So if we set it to 10, which is our x-axis, if our index exceed 10 or is 10, it will repeat back to 0 and start over. So because we have 50 points, it will do that 5 times. So it will go all the way to 9, and on the 10 one it will come back. So let's plug that to the y-axis just to preview it for a second, and let's see how it's looking. So it's doing exactly that. It's going all the way up to 9, and when it's getting to 10, it's just dropping down over and over 5 times. And if we plug it to the x-axis instead, we can see it's overlapping. So we have 0, 1, 2, 3, so on, and 10 is here, 11 is at the same spot. But now we want to take each of the points that are overlapped and just offset them by 1 on the y-axis. So to do that, let's look at our grid again. And we want to find a way to use the index to create this as well. So if the index is 0, 1, 2, 3, 4, for example, we just need the fourth one. We can say that all of these should be 1 and all of these should be 0. To do that, we can use a divide and a floor. So if we'll take the first one and the last one, and we'll divide everything by 10 by the last index we want for the row. So if we'll divide everything by 3, so the 0 will remain 0, 1 will be 0.3, 2 will be 0.6, and 3 will be 0. By 4, excuse me. If we divide everything by 4, which is the amount of points we have, 0 will remain 0, and 3 will be 0.6,
very close to 1, 0.9 or something. And 4 will be 1 because 4 divided by 4 will equal 1. And the last one, which is should be 5, 6, 7. 7 will be very close to 2. So if we translate it to what we have here, is that we have 0, and we have the last one, which is 9, the last index for the row, and we want to divide everything by our x, which is 10. So 9 divided by 10 will be 0.9, and 0 will remain 0, and 10 will be 1 eventually. And we can use this value, which the range is from 0 to 1, and the second row will be the range from 1 to 2, and can floor it. And let's just go over what floor means. So let's take a float to integer, and we have a few modes here. We have round, floor, seal, and truncate. So let's start with floor. So if we have a range between 0, 1, and 2, let's do the same for the other side. -1 and -2. Let's set the 0.5 here. So a floor will take any float and snap it to the lowest closest integer. So if I have 0.2, it will snap it to, it will output 0. And also if I have 0.7, it will output 0. But if I have 1.4, for example, it will output 1. So floor just snap every float to the lowest closest integer. So it's looking basically like that, snapping everything down. After that we have seal. Sealing is the exact opposite of floor. Seal just snap everything to the highest closest integer. So if we have 0, it should be here, 0.2, it will be 1. And if I will have 0.7, it will be 1. The next one is round. Round takes the closest, it's a combination between floor and seal, but it's rounding to the closest integer. So if I have 0.7, it will snap it to 1. If I have 0.3, it will snap it to 0. So it's looking basically something like that. Same for the negative. And the last one is truncate. Truncate is another combination between floor and seal, but truncate is the direction is set by the 0. So that means that it can use floor until it gets to 0. When it gets to 0, it will snap to seal, to the seal operation, and we snap up. So it's merging to the 0 position. Anyway, what we need here is a floor operation, because let's first of all do the divide. So let's divide our index by our x-axis, and let's set it to the y. I can see the index is going just up, all the way up to 0.9, but it doesn't reaches the 1. So you can say if it didn't reach 1, snap it back to 0. And that is what the floor is used for. Let's turn off the index beer, and we can now change the X and the Y. And if we now enable the mesh to points, you can see we have a 2D grid. Let's set it back to the values, and now we just need to set the Z-axis. So for that, we're gonna do exactly what we did in the Y-axis. The only difference is that we're gonna module everything. So let's see how to do that. If you take another integer, let's call it Z, let's set it to 3 for example, and we want to multiply everything by the 3. Let's turn off the mesh to points, and now we have all of this grid of points, and it's duplicated 3 times. Now we just need to reset them back to repeat. So how do we repeat stuff? Using module. So let's use another module, but now we want to use it to repeat the entire index before it's going to the X and the Y. We want when it reaches the end of what we set to be our grid, our 2D grid, we want to module. So let's just prove what it's doing. So you can see it's actually just repeating it. See, we have 3 lines, not exactly the same place because we're using float. Anyway, if we'll now just use the last value we set, which is 50, which is the what we have in the multiply node. Let's plug it, and you can see now we have seamless 3 times copied of our grid. Let's enable the index bear so you can see it. Yeah, we can see a few overlapping. And now we want to do exactly the same as we did last time here. So let's take a divide node, and let's divide the index by our grid. So we have index 0 all the way up to 49, and we're dividing it by 50, so this will become very close to 1, but not 1. And this value, the second here, will be 1 all the way up to very close to 2. So let's see how it's looking. If we plug it to the Z, exactly like we had with the Y, and let's floor it, and having our grid, we can multiply, add to the multiply, the X, the Y, and the Z. Let's enable our mesh to points so we can preview it better. It's working perfectly. So if you just want the 3D grid, you can just end it here, but I want to add a few more features. Let's just group it. Okay, including the index because we don't need it outside. And let's group it by pressing Ctrl G. Let's go to the group input and just organize it a little bit. Okay. So now I'm actually gonna use a cube just so I have a vector, already named vector, so I can just plug it. And let's use a separate x, y, z. Let's combine it to the x, y, and the z. And let's change the value. Okay, great. Now you will see we have a little problem, not very big one, just that it's not matching anymore. And why is that? Because we're inputting a float. See, if we set everything to an integer, it will work exactly the same. So it's just because we set it to a float. The way to fix that is actually just by rounding it, or rather sealing it. So now we're gonna use a seal value, a seal operation. So let's set it to let's test it and just set it to any value. And because we're now using inputting float, but we're setting it to integer, it's working correctly. So now we want to have the option to control the resolution, because we don't always want the size between one to another to be 1. So if I'll now add a scale node, which is a vector math, set it to scale. And I'm now gonna just say that instead of this size being 10, I want it to be, for example, 20. But for all axes, so let's plug it outside. So if I plug it to 20, to 2, it will be 20, 10, and 6. The only problem is that it's also making my grid larger, because we haven't changed the size yet. So let's do it now. If I will take, let's add a transform node, and we can now scale it down. So by how much we want to scale down? Well, we have this scale here, which is set to 2, and we scale when we are scaling by 2, we want to divide by 2. So let's take math node. Let's set it to divide, and if we're scaling by 2 and we want to divide, so we want to divide the other part by 2, so it's taking this 2 and just making it a reciprocal by applying to the lower value, and the top value should be 1. Let's plug it to the scale, and it's working correctly. Let's test it. Let's increase the scale, and we're increasing the resolution. Let's just change the scale to density. Great, we have a density factor. Now, I want to add a few more features actually. First of all, let's also output the radius, so you can change the outside of the node. Second thing is, let's add a domain. So let's go to our cube. We have our cube we used for the vector, and let's set it to the size we set. So if we now output our mesh cube, and let's change the name to domain. Let's use join geometry. So you can see we have our domain in the center of the world. We can just change it by using a transform node, and because our size is 10, from here to here, the distance. So we want to take half the distance, which is 5 in this example, and just adding to the transformation. So you basically take this corner and set it to here, for example. So let's take the vector math, set it to scale, and let's set it to 0.5, and let's set it to transform, and it's exactly in the center. Let's change the density so we see how close are we. Okay, great. So now we can see why we put it to seal and not float and not floor. So if you put the let's just take this one, set to floor. So see, when we increase the density, it's just almost getting it. But if we set it to seal, it's where right when it reaches the point when it can generate another point, it does. Anyway, now I want to add another option to fit the size. What does that mean? That means that I want to add the option to set the points exactly to the size of the domain, so to stretch them. And to do that, I'm gonna play with the size. So let's add another transform node. No, actually we had the transform node for the scale. So let's just separate it so we can use it easier. Okay. Great. By the way, it's very important to know that the reciprocal, what we have here, which is 0.5 right now, I think, now, is not just the ratio, is also it's actually the distance from one point to another. So this distance here is 0.5, and it's whatever value we put. So now it will be a quarter. So let's keep it on 2. And now, in order to use fit size, we actually want to have to use our sealed value as a vector. So let's take a combine XYZ, and let's use our sealed value to create a vector from the X, Y, and Z. Okay. So now we want to take the vector of the size. So here we have the sealed size, which is huge because it haven't been divided yet, and we have our normal size, which is the size of the domain. And what we want to do is take a vector math node. Let's set it to divide. Let's divide our size by our seal size. And if we plug it to the scale, you can see it's, wait, oh, it's working correctly. Just change this density a little bit. So if we plug the normal scale, normal density, you see it's working. Let's put an odd number. So if we plug the fit size option, see, it's almost working. The only problem is that our index is from 0 to 9, and our position is from 0 to 10, our size. So we need to subtract 1 from the seal value, and now it's working correctly. So let's change our size and density to check it out. So you see it's matching the size exactly,
And let's now change the size of, okay, so having a great grid, which is matching exactly the size we want. So now we want to change. The only problem with this option is that we don't always want it, because it's stretching the points. So the points is not actually exactly the same distance on the y-axis and z, but it's very close. So we want to have the option to fit or not fit the size. So let's use a switch node to switch between them. Let's see, set it to vector and switch between fit size and not fit size. Let's call this option fit size. Okay. We have the option to fit the size of the domain, but let's take the now we want the option to center it. Now we have the our 3D grid starting from the center point and going only to the positive axis. We want to have the option to set it to the middle of our point. So let's start to do it with the fit size option. Let's use another transform node, and when this fit size is enabled, it's very easy. We just need to take the distance, which we already know is the distance we set as the size. So let's take our size. Oops. Okay. So let's take our size and let's take a vector math, set it again to scale, and scale by minus 0.5. Half the distance and minus. So it will go to the negative. This is very simple, but if you turn off the fit size, it won't be exactly, because the origin is at the right, at the left bottom corner. So to do that, we're gonna need to do a little bit more advanced approach. So let's start by taking again our seal size, and we need to take a divide our seal size, our seal size by our density. So if we take the seal size, which if you put a easy number is 10 by 20, 10 multiplied by 2, so we have 20 here, which we want to divide by our density. So now if we plug that into the transform, oops, sorry, scale by 2. Okay, so it's almost working, but not exactly. By the way, what we need to do to center everything is taking the absolute value from from the most negative to the most positive, taking half and subtracting it. So what we're doing here is we need to find a way to find the unfitted size here. So to do that, we just take the sealed value and we divide it by the density. So overall, we just have a value, any value that we multiplied by our density, and then we sealed. So we said that it's we made it an integer, and now we are dividing it again by our density. So the density cancel each other, and we just have the sealed value. Now the problem with that is that we also need to subtract a unit, the unit of one distance here, because of what we said earlier. So if I now take a subtract again, and I will subtract this distance, this value is the distance between one point to the other, as we said, and let's test it. It's now exactly in the middle, and it doesn't matter what density we have. We can have even very low density. So this is the before and this is the after. Okay, so now we also need to switch them, which is another switch vector. We need to switch between the size and the sealed size subtracted by one distance value. We need to switch them depending on the fit size option. So when the fit size option is turned on, just a second. Okay, so when this fit size option turned on, it's going to be centered based on the size of the that we set. So let's change the density and check this out. Okay, now to actually debug that, we can use our domain. So for that, we need to, oh, just a second. We want also to have the control over the transformation. So I mean by that is we need an option, checkbox for the X, Y, and Z positive. To do that, let's add a separate X, Y, Z and a combine X, Y, Z and plug it back. Now just use a switch node, set it to float, and let's add one for each axis. And now let's plug the X, Y, and Z. Okay. Let's call it X positive and Y positive and Z positive. So it's working. Great. Now I just wanted to have the same option for the domain, which is very simple because the domain we don't need all the fit size and not fit size. We just need the opposite of what we did here. So we need to take this size and let's just take all of this section and just copy and paste it. So the separate and output it on the other side. And let's plug the positive X, Y, and Z. But now we need to invert it because the default of the domain cube is at the center. So let's take a Boolean math, set it to not just state that if the Boolean input 0, it will false, it will output true, and the opposite. So let's give it to all axes. Organize it a bit. Okay, so can target the X, Y, and Z. Great.
I think we're almost done. Check the density. Okay, it's working. Let's use the fit size. Great. The only thing left to do, let's just save the node tree and call it a 3D grid. Also, I think I have another idea for something we can do. So let's do it on the fly. For example, if I have a mesh, I want a cube, a 3D grid that is exactly in the size of our mesh, which can be useful to do points in volume or anything like that. So let's just take a Suzanne, for example, and now we want to import it into our geometry node. Let's do it inside our node group, and let's plug, let's set it to relative and not original. And now we just want to take a bounding box. Okay. And we want the bounding box to decide on the scale, on the size, so let's do that. Let's take our geometry, plug it to the geometry of the bounding box, and to get the size from one side of the Suzanne to the other, we want to use actually a subtract. So what a subtract we do is that if we have a point at minus 2 and we have a point at 2, if we now subtract one from the other, we have 4. And this is the overall distance from one to the other, and it's working, doesn't matter what value you input. So let's take a vector math, subtract, and let's subtract the maximum from the minimum. And let's plug that to the scale and the size, and it should work properly. For some reason it doesn't. Let me just check it and I'll be right back. Okay, the problem was that I used the size also in other places. Actually a lot of places. So we're gonna use need to change it in a few other places. So for now, to avoid that, I'm gonna use to disable the fit size, and it's working. Just to preview that, let's also disconnect the domain. Okay, great. Now we need to get the position. To get the position, it's a similar method of just taking the maximum and minimum. The center is basically the average of the maximum and minimum. So we have a point here and we have a point here. The average will be the center. So let's take the minimum and maximum and plug it to an add. And let's now use a scale to scale it by 0.5. So if you have a value of, for example, 3 and a value of 5, the average will be 4, so we can just add 3 to 5 equal 8, and we divide 8 by 2, it will be 4. So that is the center, and we can use the center to transform. Here we have the transform. Let's add another transform and let's transform it. This is a very long shot, but yeah, and it's exactly in the size of our Suzanne. We can now change the Suzanne size to whatever we want. Now there are a few things we need to do to make it work in any situation. First of all, I want to also have the option to control the size. So let's just connect the geometry so we can use it outside of the node. Let's drag back the Suzanne, set it to relative, and in the node tree, let's promote it just below the size. Let's call it geometry cage. And now we want the option to switch between the size and the cage. So let's use a switch node. Switch between vector. Now there's a pretty funny trick which is actually working. Let's switch between the cage also. Yeah, let's do that later. So I'm gonna add domain size and just input the domain size, and I'm gonna use a math. You can use an add. So if we add a point count and oops, wrong shortcut. Let's duplicate it. So we have the amount of points. If it's a curve, we have the amount of spline point count for the for a curve. And let's duplicate it again. Make it instances. The amount of instances actually, and one last time in case we have point cloud. So if we have anything here, let's take a compare node. You know what, let's delete the instances because we don't mess with instances when we are using bounding box. Anyway, and when you have any kind of geometry type and it's and the value is larger than 0, which when we have something plugged to the geometry cage, then I want you to switch. So right now it's switching because we have something plugged. If we disconnect it, it will go back to the size we set. Okay, so let's use the same here for everything that is related to the size actually. So this is instead of a size. Yeah, so we need to plug that to everything that has to do with size. So to here and to here. Let's just plug that instead. And it's pretty far out, but we need to organize it just a little bit. Okay, great. We might have more problems with that. I'm not sure at the moment. Oh, yeah, by the way, when we're using the cage, we can't use the positive XYZ. It should be off, because otherwise it's actually destroying the center. So we need to get the positive. Let's also connect that to make it easier. Also have the size here. Okay, so we actually don't need that. So it should be zeros. Let's take another switch node and switch boolean to be 0, depend on let's put it to the false. Okay. Okay, so we can switch between those. Based on the if there is or there is not any subject. So let's put it to the true socket. And if there is no geometry, we can use positive. Wait, it's not working. Let's add a boolean math, set it to on, set it to true. So we can use, wait. Okay, so almost correct. The only thing we had to do is to flip it. So in this case, we don't have the geometry cage enabled. So if we do have the geometry nodes, the geometry cage turned on, it will switch to false, which means it will use the option to center the grid. If we don't have, it will take whatever value we use in the positive x, y, and z. So let's try that. Let's just take the geometry. If we plug the geometry cage, it works. If we disconnect it, it's going back to our control. So it doesn't have any effect when the geometry cage is on. It should also work with the fit size. Yes, it does. And with our domain, it does not, because we didn't plug the domain. So we just need to take our position, let's duplicate transform node and take the, let's take a reroute and take our midpoint all the way up here, plug it to the transform node. And we shouldn't need an option for when it's on and off, because it should be exactly nothing. It should be 0. Okay. So now I can also plug a domain cage. Let's change the size of Suzanne. And it's working with fit size and every other option we want. Great. Change the density? Yes. Okay, that is great. So that is, I think, everything. Yeah. Wait, before wrapping everything up, while I was editing the video, I realized that I didn't show any project, render, or any use of 3D grid, although it might be obvious. So I spent some time trying different cool cinematics renders, and I made a cute little animation. Enjoy! Let's do a little breakdown. In this render I added a Suzanne mesh, pushed it out a bit by the normals to give it some more volume. Then I used the geometry cage option for Suzanne, and because I wanted the cubes to blend seamlessly together, I turned off the fit size option to get consistent distance between the points. Then removed the extras with the inside node, which I didn't cover in this video. translated, scaled, and added some more effects to the instances based on the index and current frame. A little tip here, to animate things based on index and time, you just need to subtract one from another. After the animation was done, I animated the cameras, enabled motion blur, depth of field, and set the focal length. Created this material for the instances, which is just two emission shaders and a glass shader mixed based on a layer weight node. Then transition to glass, and then when the instance reaches its position, it turns black. In compositing, it was just a glare node exported to PNG, combined everything with some sound effects, and that's it. Just a reminder that we have the index. The index we have is actually very well organized, and we're just running X, Y, and then Z. To know what type of videos you're interested in, I'm thinking to make a video about the fundamentals of math and geometry nodes to understand the core principles. But I know that some people also want to see all kind of effects and such, like the fireman I made, and other kind of visual effects, and maybe a pretty scene and cinematic scene ideas. So you can comment below if you want to understand notes and how they work versus seeing visual effects tutorials and everything in this kind of topic. Or you can actually comment on any other topic you want me to cover in Blender and 3D, and feel free to do that. So also, as I said, I have this 3D grid also in my preset to create 3D grids, and this now in alpha stages, the H nodes. But you will see this add-on, I hope, very soon, already out there, getting with more and more nodes as we go. So thank you for watching, and hope this was useful, and see you next time.